This is all implemented in ease, of course, as everything is, I think. So in ease, we would go to our function information, go to heat transfer and fluid flow, and then there's a whole heat exchangers dropdown. So in our heat exchangers dropdown, I think we showed this a little bit last time, but you'll see that there's different options. So maybe now this makes a little bit more sense. So we have NTU, we can get our NTU in terms of effectiveness, or we could get effectiveness in terms of NTU. It's calling the same underlying equations, but it's going to return, one of the other things, depending on what you tell it. So here we could say, let's say we wanted to get effectiveness back, given an NTU. Now we come in here and we pick our flow configuration. So this is counterflow. You can flip through and see this is parallel flow. They're both going in the same direction. Here we have cross flow with unmixed, cross flow with mixed, right? Cross flow both mixed. Here's our shell and tube. So you can start getting these different configurations, and these all line up, or should line up, exactly with the solutions that you get in this table. It's just that they're implemented in a useful form. So you'd come in here and you'd need to specify, let's say, the NTU. So you calculate the NTU, you calculate the C dots, and you tell it you want to get back to effectiveness, and it does that for you. So those are all there. Let's see if there's anything else to point out. Yeah, so if you did want, or say some older engineer comes to you and says, what about the LMTD solution? You can do that too. You just have to learn how to use it. But those are also implemented here. Not that I have anything against older engineers. All right, so let's see, we have a couple minutes left. Let's just talk through a little bit about the behavior that you would expect for these types of heat exchangers. So what we're showing here on these plots, let's just pick one to start. So if I were to plot out, as a function of number of transfer units, my effectiveness. So what am I doing? I'm plotting here on the x-axis my non-dimensional size. And so as I go up this way, my heat exchanger is getting bigger compared to the C dot in the system. So I plot effectiveness as a function of that. How would you expect effectiveness to change as a function of heat exchanger size? You'd expect it to go up with heat exchanger size, right? That makes sense. So what do we see here? We see this is now, this is a counterflow arrangement. And so you see down here, if it's a really small heat exchanger, they all kind of look about the same. And then as you get larger and larger, you start to differentiate a little bit based on the capacitance ratio. So if I have a perfectly balanced heat exchanger, C dot H equals C dot C, that's going to follow this line here. Your effectiveness at the outlet is going to be, or effectiveness as a function of size, is going to be smaller than it would be if it was an unbalanced heat exchanger. And so, right, this is one of the features of the counterflow heat exchanger. But you can see as you get to CR of 0, that's really the only time when you could get like a perfectly effective heat exchanger, unless you take NTU all the way out to infinity. But once you go to NTU equals infinity, these all converge to 1. Right. So this is one plot in terms of counterflow, but you do see also that, right, you can get effectiveness much higher than say 0.5. Right? You can get pretty good effective heat exchangers as opposed to parallel flow heat exchanger, where if you have a perfectly balanced parallel flow heat exchanger, what are you doing, right? You have, so we could plot it like this, right? You have your temperature coming in. This would maybe be TH, this would be TC. If it's perfectly balanced, your capacitance rates are equal to each other, what would you expect the temperature to look like? It would be hot coming in like this, and cold coming in like this. And they all converge to each other at the outlet. If it's perfectly balanced, that's going to be exactly halfway, right? Exactly halfway between those two temperatures. If it's unbalanced, maybe this convergence point will shift up and down a little bit. If it's CR equals to 0, then what I'm saying is I'm coming in, let's say my hot doesn't change at all. It's got a very, very high capacitance rate compared to my cold. So my hot temperature is not changing at all. Then my cold temperature would look something like Or it could look something like this. Right? Then I could get an effectiveness approaching 1, which is what you see for CR equals 0. So you see these different plots as a function of size, different capacitance ratios. That's how they kind of behave. And then for the cross flow, it's kind of somewhere between those two things. So you have the counter flow is always the best you can do. Right? Parallel flow is always the worst you can do. Cross flow is going to be somewhere in between. One other thing to point out, right? Last thing I'll point out. If you're designing a heat exchanger and you calculate your NTU, which you should do, you will hopefully find that your NTU is in what we call a reasonable range. So if I was designing a heat exchanger and I calculated an NTU of say 0.1, what would that tell me about my design? It'd tell me I could make my heat exchanger marginally bigger, just a little bit bigger, and get a huge gain in performance. So why wouldn't you add a little bit of extra area if you're down here? You get a lot better performance. If you design your heat exchanger and you're finding NTUs like 50, that says something about the design too. It says you're kind of wasting your money on your heat exchanger. You're all the way out here where an additional unit of heat exchanger is not actually changing your solution at all, right? It's just your effectiveness is what it is. It's not changing really very strongly at all. So when you're designing, you almost always should find yourself in this kind of sweet spot here, right around the corner of these graphs. NTU of 2, 3, 4, something like that. So this is a rule of thumb.